So we are looking at this problem of finding local minima in a grid. You are given a grid G n cross n integers, and you have to find a cell which has value smaller than all the 4 neighbors in the 4 directions. For example, here the green cell has 3. So this local minima always exists. You can trivially find it in order n square time, but we want to do it in order n. So we started with this solution for one-dimensional array. And so we prove this theorem in blue, that we give this binary search based algorithm which finds local minima in an array of size n in log n steps. Okay, so this is the brilliant thing here, is that it doesn't depend on sorting. So the array is a random array, any order, but still this idea of looking at midpoint and then halving the size of the array, you are able to decide first of all which side to go, and then there is an invariant we found. So the invariant was that a local minima is present in the half that we pick. So for that we had, mainly it was this lemma 2. Lemma 2 says that when we identify this LR, when we change this, the endpoints L and R, we are always making an improvement. So basically the AL value is smaller than the neighbor and AR value is smaller than its respective neighbor. So there were 2 boundary points. Then we go to the grid situation, which is this, this picture. So now we look at the mid column out of n columns, and there we find the minimum, which is the green cell, shaded cell, and we decide amongst these 2 red neighbors which one is smaller, and we move to that side. So again you change L and R. In this example we changed R and brought it back. So basically pick the left half. L we did not change in this. And the proof was by this argument given in blue here, that minima in min minus 1, even if it is somewhere else, it is smaller than the red cell, which in turn is smaller than the green cell, which is the smallest in the whole boundary of mid. Okay, so that was the proof that we are maintaining local minima somewhere in this half. And that gave us a n log n result. So we get this theorem that local minima in the grid can be found in n log n time, which is still not good enough. We want order n, right? So that we'll finish in this class. And the idea will be that previous analysis was doing sigma n, I going from 1 to log n, and that is why we got n times log. We'll reduce this summoned n, we'll halve it every time. So for which we have to now halve the rows also. So we take middle column and middle row. This directly will not work, so we have to change the pseudocode. Any questions till now? So this was an exercise for you. Find the counter example or the bad instance if you directly move from mid column to mid row. Okay, so you alternate between mid column, mid row, again there mid column, mid row. That will not work, because the problem is that this green cell which you are identifying, that only satisfies a property either with respect to the 2 columns or with respect to the 2 rows. What you want is a property which is for both simultaneously for the two rows and the two columns. So in other words, we now want an invariant instead we want a more general invariant for all the borders. So all the borders means that basically the box. So we want a guarantee, or the invariant has to be that when we move to, so what are the endpoints? So the endpoints here are left, right, and up and down. Okay, so this quadrant marked by L, R, U, and D. Whenever you move to such a submatrix, there should be an element X here. You should ensure the invariant that there is an element X which is smaller than all the elements in the green shaded part. Okay, so instead of like in the previous idea, what we were having was either only the L and R columns are bigger than X, or when you move to the row case, U and D rows are smaller than X. But we want this simultaneously now. So we want the full boundary to be greater than, which means every cell in the full boundary should have value greater than X. There should be an X. So that's the question. Does there exist an X such that X is less than each element in the border? Okay, so we have to change the pseudocode so that this invariant is maintained. Is that clear? Any question about this idea? So essentially this if you look at this lemma here, this star means that if you go left to your L, that border, and the second star means this G star R plus 1, if you go right side of R, that full border. So this lemma is only talking about the vertical borders, and the symmetric version for row will only talk about the row borders. Now we want all of them, right? So we will have essentially four inequalities with X being in the middle, and the stars being for those two column and two rows. So I'm not giving the details of that, but you can imagine how it will work. So all I have to show you now is the pseudocode, or how to modify the pseudocode so that this is preserved at every induction step. So we need to change the algorithm only slightly. To ensure the existence of this X. In each induction step or recursion step. So let us see that. So I'll not give you the full pseudocode because the full thing is pretty big. I mean, we have gone through many ideas. Let us only focus on the important part. So for the important part, let us see in the picture first before I write something. So your markers LR are here, up, left, right, up and down are here, and the outside is this, immediate outside, which is the border. And from the previous iteration or recursive call, there is a guarantee. You have the invariant that this between LR UD, you have an element that is local minima. Oh, sorry, which is smaller than every green cell. Okay, there is an X inside which is smaller than every green cell, which means the four spaces which I have drawn in green. Okay, so this has many cells. I mean, it has around 4n cells. So each of these 4n cells has a value which is bigger than this distinguished element X, which lies inside. That's the invariant. Now, when you decide to change the boundary, so suppose you will look at so in the next step, what will you do is you will look at the mid. So mid is somewhere here. And in the mid, you will find the min element, which is somewhere here, right? And the same pseudocode as before, which was find in the mid column, find the min element. I mean, a minimum means it's a global minimum in that column. Okay, find the element, this green element, which is smaller than every element in the mid column. And look at the neighbors. And suppose this neighbor is the one which is smaller. So in the previous pseudocode, we said that when this red cell is smaller, we will take the left half, right? Which means that R will now be set to mid, or sorry, mid minus 1. So this is mid minus 1. And L won't be changed. That was our step, but that will not guarantee the invariant that we want, the new invariant. So instead, what should be done is you should actually keep track of the element X, which is there inside, and compare the element X with this red element. Now, if the red element is smaller than X, then it is fine to go along with the old pseudocode. But in case X is smaller and it lies on the other side, which means it is on this side, for example, here if X lies, then you should go the other side. Okay, even though the neighbor red of green is smaller, you should not take the left half, you should take the right half. So we'll yeah, so I have to actually write it to clarify. So basically a third point has to be stored. For now, you just remember that our correction in the pseudocode will be that we will not have just two things to compare, or well, we had previously we had these three things. Now we'll have four things. We'll have some other point also that we'll be keeping track of, and our decision will be a bit more complicated than before, which side to pick. So how the decision is made, we'll write it down. So let me first take the base case. Let's see the base case first. So in the base case, L and maybe U, these are 0, and R and D is n minus 1. So this orange part is actually empty. Okay, this won't exist in the base case because your green boundary is actually already the absolute boundary of your grid. So there is nothing outside. And clearly in the base case, the invariant is true because whatever element you have inside. There is no element outside. So in this case, when you will look at the middle column, how do you decide which way to move? Should I move on the left half or the right half? So let's check that decision. So here what we will do is we will compare I also want that row. So let's call that row R, where the minimum lived in the middle column, mid column. So compare GR mid maybe I should change the notation a bit. Let me call this now mid column because there will also be a mid row. So compare this red element, the right red element, which is GR mid C plus 1, which we were doing anyways in the previous pseudocode, and we were picking the minimum. Now we will keep track of another element, which in the base case, let us just pick. For lack of options, let's just pick this element. This element here, let's call it P. So this element P, which is simply U comma L. Okay, so we'll compare the two red cells which are neighbors of green cell and also the corner, the top left corner of the left half of this matrix, of this grid. And move to the half where the min lies. and update P to this min. Okay, so this is the only change in the previous algorithm. Okay, it's a very small change, but to analyze this, you have to think hard. Why will it work? So what this is doing is it is looking at the two red cells as before, but it is also looking at another cell which we are now storing, which in the base case will simply be the top left corner. So that's the U comma L entry, which in the beginning is basically 0 comma 0. In the base case, you are looking at the 0 comma 0 entry. And out of these three values, you will go to the half where the smallest is stored. So this may behave opposite to your previous algorithm, because it is possible that the minimum was in the right red cell amongst the two neighbors, but the 0 comma 0 entry is even smaller. So you will violate the previous algorithm and go with the left half still. Okay, so this is the place where this pseudocode differs from the previous pseudocode, because you have now this third value. So if it is smaller, then it will dictate a different move. Okay, so this may be in contradiction with the previous pseudocode, but the good thing is that this change now will ensure our invariant, the new invariant. Is that clear? Well, first of all, is it clear what the pseudocode is now doing? What is the difference between this and the previous algorithm? If that is clear, then do you see why this is good? So yeah, so stay in the base case first. In the base case, you have no orange boundary anyways. So the 0 comma 0 entry was vacuously smaller than everything outside, because there is no outside element. So now, so is it possible for you to analyze this first step? So now when we look at the middle column, say so this blue cell, and let me remove this X now. Instead of X, I'll use this P. So say this blue cell happens to be smaller than the, I mean, there are these three, right? So let's number them for simplicity. So this one is, let's say this one is M. This is M2. This red one is M1. And this blue one is M3. So say M3 is smaller than both M1 and M2. Okay, so in that case, the previous pseudocode would have said that you should pick the right half, right? Which would have been fine for the old invariant. It may not be fine for the new invariant. It may be insufficient. So the new invariant also considers this point P, the 0 comma 0 element. Now if the 0 element is smaller than M3, then it will instead pick the left half. Okay? That's what this is doing. So if P is less than M3, and M3 is less than both M1 and M2, still we pick the left half and not the right half. So which is unlike the first algo. Okay, so in case this magical point P, this extra point P is smaller than the smallest of these three in row R, then you have to pick the left half instead of going with M3. Because the advantage is that when you pick the left half, you have an element which is smaller than these boundaries. So the boundary on top, so let me call it north, the east, the south. Okay, so the point P is already smaller than all the cells in the north, east, and south boundaries. I mean, vacuously, because you are in the base case, so orange is actually empty. Moreover, the new west that you are introducing here, so you are shifting the original west to this west. In this boundary also, every cell is bigger than P. Okay, so this is the only case which you have to understand. From the picture, you see that we have made sure that there is a point, namely here we have defined it to be P. Already we have this P available, that is smaller than the north, east, and south cells. And now when we make mid C as the new western boundary, every cell there is bigger than P, right? Because P is smaller than M2, and every other point is smaller than M2 because of that relationship. So here every point is smaller than M2, and P is also smaller than M2. In fact, P is smaller than M3, so clearly it is smaller than M2. So P happens to be smaller than everything. Okay, it's smaller than M1, M2, M3, so it is smaller than, here we had picked least, so this is greater than. Yeah, so P is smaller than M2 and M2 is smaller than every other thing. So in the western boundary, now you have also this property that this particular P is smaller than west, so which means that P is smaller than all the four boundaries. So P is smaller than each of the cells in north, east, south, and west. So this is, in base case, this part is vacuous. While the western part, we are ensuring, I may have messed up the directions, sorry. So, yeah, north, west, and south are by vacuous in the base case. And the eastern part we have covered by the pseudocode. Okay, so for the eastern part, because the eastern border is which is actually moving towards the west, so for that border, we have a more intricate pseudocode. Yeah, so how do you move one step from the base case? I have analyzed here in the pictures. And once you have covered the base case, every other induction step is symmetric. It will be very similar, it will be identical to this argument. Okay, so induction step and base case I've covered at once for you in this analysis. So this means that we have covered the base case, and the next case. By finishing the induction step. So it is identical not only when you pick middle column, it will also be identical when you pick the middle row. Okay, all those things are just cases. So base case is vacuously true, and next case is true by this induction step. And once you have seen the induction step over the base case, you can see that the same argument works always. Okay, because when you have the reason why it will work in general is because the point P we are updating. So whatever point P we find, which is kind of a certificate that the half that we have picked satisfies the invariant, we store that P, and next time we have the comparison with the stored P. So just that important note that P gets updated. In each induction step. So it certifies the invariant property. Okay, so the invariant property is this. This is the invariant. Okay, so the invariant is that there will always be an x available that is smaller than all the north, south, west, east borders. So maybe I put that here as P also, so that you have a handle on that. So this P will actually maintain in every induction step. So at least this P will work. There may be more points, but one point we have identified in our pseudocode. Is that clear? So that's the modification. It may be too clever for some of you. So you have to go home and actually understand what happened here. But all the main parts of the proof are written down. So that's the pseudocode fragment. Let me call it 1. And just to complete it, the next pseudocode fragment is one more thing you have to add, which was completely absent in the old pseudocode, which is that you also have to look at mid-row. Right? Instead of drawing pictures with columns, you also have to draw pictures where you pick the middle row. So you have to alternate between mid-column and mid-row. So repeat the above fragment with the middle row So middle row is the up plus down pointers by 2. Okay, so instead of L plus R by 2, you do U plus D by 2. So that gives you the middle row. And do the same fragment as you did before. Okay, this fragment, now you have to take a transpose of this image and give those three elements, and that is the set S, and then you have to take P to be min of S. So you do it for column, you do it for row, and then you again do it for column, again for row, and so on. Okay, this is the full algorithm. So fragment 1, then you do fragment 2, and then you repeat. So you repeat till this left and right, till you have a 1 cross 1 grid basically. Right, because now you are reducing both the dimensions. You will reduce the number of columns, and then you will reduce number of rows. So ultimately you will actually reach a point where L is equal to R and U is equal to D. So you now have a 1 cross 1 grid. So that's your element. That's the local minima. So repeat till you get a 1 cross 1 grid, and that's the output. Okay, so you have to maybe you write this pseudocode in full and then check for the invariant condition that I've stated. Formally prove it so that you are satisfied that everything works. So now let us move to the time complexity. So what this pseudocode will show or achieve is that local minima in the grid with n cross n elements is computable in it runs in linear time. So why is that? So idea here is main idea is it's divide and conquer in 2 dimensions. Okay, so we are dividing the columns by half, and we are also dividing the rows by half, and so on. So which means that the number of iterations remains log n, but that is not enough for the analysis because that property we had before also. Right? Before also we had this analysis. I was equal to log n, so the number of rounds in the induction step was before also log n, but the thing that we wanted to reduce is that n, the summoned n there, we wanted to reduce it. We wanted to halve that every time. So we will show this n by 2 raised to I. Okay, that's the idea of the contained in the new algorithm, that when you are trying to find the minimum in either mid C or mid R, that minimum can be found in time n by 2 raised to I. Why is that? Well, because that is the length of mid-C or mid-R. After I steps, since you are halving in both the dimensions, the 1D array where you want to find the minimum is only of that much size and not n size. Okay, so that's all. So we have this inequality, we have the time complexity. So well, for the correctness, the invariant make sure that the final 1 cross 1 grid is a local minima. Why is that? Well, because you have now this, ultimately you have just one cell, and the boundary are these 4 neighbors, right? And since at every induction step invariant holds, ultimately at the end when you are left with only one cell, there also the invariant holds, which means that the green cell's value is smaller than its 4 neighbors, right? This is the definition of local minima. So invariant makes sure that what you output will be correct. So there is no issue with correctness. As long as you believe the invariant, the answer is correct. Time complexity is more complicated. So for time complexity, you have to write down so number of steps is when you are doing the ith halving, either on column or respectively row. Then since you start with n cross n grid, and after 2 halvings you are in n by 2 cross n by 2 grid, and after 4 halvings you are in n by 4 times n by 4 grid. So you have to basically find minima, or which is actually global min, in n by 2 raised to I grid array. Right, so which comes down to this much time. Question? N upon? Yeah, so the big O hides all that. I minus 1 means that you are either halving or doubling, so all that is hidden in the constant. So let's not go into those minor things, because I already said big O, and this is now an equality. So it is sigma I going from 1 to log n, but the linear search is actually only on a small array, so which is n by 2 raised to I time. So this, when you work out, this comes out to be order n. Okay, that's the proof. So the lion's share of this complexity comes from finding the global minima in a 1D array. But the array we are halving. Okay, so it becomes a linear time algorithm for local minima in a grid. Any questions?
The second one, when we had a box, and we found a global minimum, like when we switched to the left side, we have missed if there was a global minimum on the other.
Sorry, I did not understand. Where is the question here? On this slide or previous slide? Previous. Okay. Yeah, we compared this, the S set. There is an S set which is important here. So this S set has 3 elements, and we find the minima and we move to that side, whatever it is, left half, right half. What is the question? No, it's not. We are not trying to find an element which is smaller than everything. The invariant is just that the box which I have currently, within that there is an element which is smaller than all the boundary elements. So that choice may also be there on the half which we have skipped, but we don't care. We only care about the half that we have picked. And we keep the certificate point P. Point P is a certificate that we are correct. It may also work with the other half, but that isn't our concern. I just want to maintain the invariant, that's all. And the time here is, in finding this green cell, you have to compute the global minima in 1D array. But fortunately for you, that 1D array is halving every 2 induction steps. Okay, so that is it. Yeah, unless you have any further questions. So you have to practice proofs of correctness. Identifying invariant. And analyze the recurrence. To derive the time complexity. Okay, so in this example, which ran over almost 3 hours, you must have seen the ideas of the algorithm. Based on that, you have to give the pseudocode, but that is not enough. Okay, just the pseudocode is not enough because there are no test cases or input instances given here. So it's not that this pseudocode will work on one example. You have to actually show that it works on all input instances. So for that, you have to basically identify an invariant. You have to give a proof of correctness that that invariant is actually maintained throughout the execution of the algorithm. And then to actually say something about the time complexity, you have to give a recurrence and analyze it. Okay, so in this case, recurrence is kind of already in expanded form. We have already unfolded it and given you n plus n by 2 plus n by 4 and so on. So this ultimately this proof is by geometric progression. So it's a GP proof. The recurrence is completely unfolded and you get the answer order in. So these are the steps which you will see again and again in all the problems that we'll solve in this course.